Welcome to November 15th LeetCode Challenge. Count complete tree nodes. Given the root of a complete binary tree, return the number of nodes in the tree. According to Wikipedia, every level, except possibly the last, is completely filled in a complete binary tree, and all nodes in the last level are as far as left as possible. It can have between 1 and 2 to the h nodes inclusive at the last level h. Design an algorithm that runs in less than big of n time complexity, linear time complexity. So this is a pretty easy question. The only hard part is this part right here. Design an algorithm that runs in less than linear time complexity. So basically, if you have a binary tree here, we want to know if it's complete. So we want to basically know the number of nodes in the binary tree that it's complete. So there's 6 nodes in this binary tree, therefore return 6. If it's 0, return 0. If it's 1, return 1. If it's empty, return 0, I should say. So the numbers of nodes in the tree is ranged between 1 to 5 times 10 to the 4. The value of each node is between 1 to 5 times 10 to the 4. And it's guaranteed the tree is to be complete. Alright. So to solve this is actually to solve this using the following restriction is actually quite mediumly challenged. However, we could just solve it, I guess, using recursively maybe. Let's try that. So obviously, if we were to solve this using a breadth first search or a depth first search, we can actually do this quite easily. But let's try to solve it using the breadth. Actually, let's try it out. So if we were to use this if we were to solve this linearly using a depth first search, we'd use something like return 1 plus the self recursively call count nodes, and we pass in root.left, and then we concatenate that with self.count nodes recursively call root.right. Else, if not root, else return else will be 0. And this will be essentially giving you the answer. So basically gives you the count of basically 1 plus the number of nodes on the left side recursively called, plus the number of nodes on the right side recursively called. If it does not exist, then return 0. So this is a depth first search one-liner. Oh, there's something not right here. If not root. Run that. Oh, what am I doing? If root, else 0. Oops. This should work. Okay, this is a depth first search. However, it's running recursively at big of n time complexity. So it's not what is being asked for. Let's kind of use this idea though to solve it using less time. So the solution will probably employ the complete tree, and we want to find the children of a complete tree that's also a complete tree. So therefore, what we could do is basically, by completing a tree, traversing the tree, we're given, basically, let's give a constraint that we know that the main tree is completed. Therefore, both the children have to also be completed. So then we could just run that as such. So let's say if not root, return 0. Then we can define left, define right as L and R. We're going to define 4 variables, and we'll call that root.left, root.right, and we're going to have values of left L and R to be 1 and 1. So basically you compute both the left and right heights of each subtree going all the way down to the left and right nodes. So we have that defined so far, this constant space so far. So while left, we are going to swap the left and L to be left dot left and L plus 1. While right, we'll swap right and R to be right dot right and R plus 1. Now, once left L equals right R, then we just return the height, which is going to be, if it's a full tree, then we know that the size is known. Therefore, we know that we have between the size of it will be 2 to the h, right? And for each here, we could just do 2 to the power of L minus 1. And that will be the algorithm. And then from that, we just essentially do what we did before for our depth first search. We just return this recursive call between 1 plus self dot count nodes on the left side, root dot left, plus self dot count nodes on the right side, root dot left, right, I mean. Alright, run this. So, this is pretty similar to the last one. However, it should be a lot quicker because we only run through the algorithm. Yeah, it's a lot quicker. So basically, the solution employs the main property that the complete tree is namely that the tree of a child is a complete tree also. So it's also a complete tree. So that would mean that by traversing the tree, it is trivial to know that basically, given the constraint that a tree is a complete tree, guaranteed, then what we could do is that we know that the main property of a complete tree is both of its children are also complete trees. Thus, we can quickly find that big O of log n time complexity to check whether this tree is complete. It's also a full tree as well that's being filled. So we can compare the left height to the right height for a full tree. So therefore, we know that the depth. So we know that the size of the tree is known. Therefore, we know that we can return to the power of the depth of the tree minus 1. So that would mean that the time complexity of this is big O of log n times log of n, which is less than log of n, less than n. And with the space complexity is also big O of log of n. And that's the hard part there. Alright, that is it. Have a great day, everyone.